Welcome to Study Loop.
So in this problem, we are given a reaction of the decomposition of NOBr, which is nitrosyl bromide, which decomposes to give us nitric oxide and bromine. So we are given the volume of the reaction vessel as 5.0 liter. Then we given the temperature of the reaction as 100 degrees C, which in Kelvin scale will be 270 373 Kelvin, and we are given the mass of each of the component here. For NOBr, the mass is 3.22 gram. For NO, so these are the equilibrium masses. So for NO, the equilibrium mass is 3.08 gram, and for bromine, the mass is 4.19 gram is the equilibrium mass. So these are the data which are given in this reaction. So in first part of this problem, we have to find out the equilibrium constant expression Kc for this reaction. So as we know that if we write down the equilibrium constant expression for this reaction, we will write, so as we know that the equilibrium constant is in the numerator, it contains the concentration of the products. So the product is NO and we have 2 NO, that means 2 will be as a power of NO, and then we have bromine. So this is the bromine concentration, and in the as the denominator we will have the concentration of the reactant, which is NOBr, and since we have 2 NOBr, the 2 will go as a power. So this is the Kc expression for this. So here all these things are actually the concentration of the products and reactants. So first you have to know the concentration of each of the reactant and products to find out the value of Kc. And again, the concentration is equal to number of mole over volume. So we know the volume of the reaction vessel, which is given as 5 liter, but we don't know the number of moles. We are given the mass of each of the components present, and from their masses we can find the molar mass of each of the components. So we'll first find the number of mole of each of these. So number of mole of NOBr will be, as you know, the number of mole is mass over molar mass. So the mass of NOBr is 3.22 gram over the molar mass of this is 109.92 gram per mole, and this will give us a value of 0.029 mole. So similarly, if we just divide each mass by their molar mass, for NO, the mass is again it is 3.08, and its molar mass is 30.01 gram per mole, which will give us a value of 0.103 mole. And finally, for bromine, the number of mole will be, so it's 4.19 gram over the molar mass of bromine, 159.808 gram per mole, and this will give us a value of 0.0058 mole. So these are the number of moles for each of the components present. Now we will divide each number of moles by the volume, which is 5 liter, to get the concentration of each of these. So if we just divide each number of moles by the volume, we'll get the concentration for each of them, and in this way the concentration of NOBr will find as 0. 0.0058 mole per liter or molar. So just simply divided uh, for NBr2, the number of mole is not this, it's 0. For Br2, the number of mole is 0.026 mole. All right, now we are dividing each number of moles by the volume to get their concentration. So the concentration NOBr will be 0.0058. Then the concentration of NO by dividing number of moles of this by its by the volume will have 0.0206 mole. And then similarly, we'll find the concentration of bromine by dividing its number of moles by the volume, which is 0.0052. So these are the number of the concentrations for each of the component present in this reaction mixture. Now we can just plug these values here in this case C. So we'll just plug the values of concentration for each one, and if we do that, we'll find the Kc value as 1.90 times 10 to the power minus 4. So this is the value of the Kc for this reaction. Now in second part of this problem, we have to find out the total pressure exerted by the mixture of gases. So for finding out the total pressure, we have to find out the pressure exerted by each component, and we can do that by using the ideal gas law, which gives us ideal gas equation PV equal to nRT. And from here, if we just rearrange this equation as P, we just put V on the other side, it will be N over V times RT. And again, this N by V is our concentration, which you have calculated as this. So N by V is concentration. We can write this as CRT. That means pressure is equal to concentration times the universal gas constant and the temperature. So let's find out the pressure for each one. For NOBr, it will be the concentration of NOBr, which we have calculated as 0.0058 molar or mole per liter times the universal gas constant in a liter atm unit, which will be 0.0820 liter atm per mole per Kelvin times the temperature, which is 373 Kelvin, which is given as 100 degrees C, which in Kelvin scale will be 373 Kelvin. And in this way, we can find the pressure of the NOBr, which is 0.1774 atm, atmospheric pressure. So this is the pressure of NOBr. And similarly, you can find the pressure of NO if we just multiply the concentration of NO by the universal gas constant and the temperature, we'll get the pressure of NO as 0.6301 atm, atmospheric pressure. And then for bromine, it will be 0.1590 atmospheric pressure. So these are three pressures for exerted by each of the component. That means the total pressure will be simply the sum of these three, and if we just add these three together, we'll get a value of 0.9665 atm. So this is the pressure exerted by all the components, or the total pressure exerted by the mixture of gases. And then in part C, we have to find out the mass of the original sample of NOBr. So the mass of the original sample of NOBr will be simply the sum of the masses of the equilibrium components, since in a reaction we know that no mass is lost. And so the amount of product we have here is basically the amount of the reactant which was initial in the reaction mixture. That means the total mass of NOBr, which is the reactant, will be equal to the sum of all the equilibrium masses. That means 3.22 gram plus 4.19 gram plus 3.08 gram. So the total will give us value of 10.49 gram. So this is the total mass of the equilibrium components, and since this is the total mass of the equilibrium component, that means this is also the initial mass or the original mass of the reactant NOBr.